Welcome to today's video. Today we're going to learn about the affine connection, the covariant derivative, and how to use them. Notions that are extremely important for what's coming later. Before getting a more rigorous introduction to the notion of covariant derivative, let us understand a little bit why we need a notion of covariant derivative. Because you may say, oh, but you already have something called Lie derivative. What do you even need the covariant derivative to talk about directional derivatives and variations of tensor fields in a given manifold? Well, let me pose the problem in the following way. Now, given a function f, I know what it means to take the derivative of f with respect to, if you want, in this case, the coordinates, right, of the manifold, with respect to a point in the manifold in a coordinate basis like this. I just take a derivative of f with respect to x mu, well, it's just partial mu f, no problem. That's defined unequivocally, right? That's, in fact, you would say, oh, those are the components of the differential. In fact, the differential of f, right, is partial mu f dx mu, right? So those are the components of the differential of the function. Now the question we ask now is, what does it mean to take something like that? I want to take the derivative now of a vector. Not the components of the vector, the vector, the whole vector. What does that mean? And that question is non-trivial, because maybe one answer that you want to give, perhaps, is this one, right? Let me write a question mark here. Some object like that, I don't even know what an object means, but maybe let's make sense of it like this. Maybe I just take, because the vector is like that, I just take the derivative of the components, maybe let's write it with a nu to change the index, the components of the vector, right, with respect to x mu, epsilon mu, right? Just, you know, the derivative of this is like kind of the gradient. In fact, we could write that with the symbol we usually use for gradient in calculus of the vector v. Perhaps we want to write it like that. And this is what you would do in Cartesian coordinates. Now, several problems with that. First problem, maybe out of your memory you remember that, yeah, the gradient was that when we worked in Cartesian coordinates, but it wasn't like that when we worked in spherical coordinates, right? If you remember, in spherical coordinates, the gradient had extra terms. It's not just the partial derivatives of the three components in r, theta, and phi. So there's something going on there, right? To begin with. To continue on, that thing is not a tensor. So the vector is a tensor, is one's contravariant, but if I do this thing, if I try to transform with the changes of basis, this thing is not going to transform like an object that has one more index downstairs, which should be an object that is one's covariant, one's contravariant. This object, built like this, would not be a tensor. It's missing something. Why is it missing? Well, think of it, for example, in the case of spherical coordinates, the way they taught it to you in calculus. In calculus, they tell you, right, the three vectors of the basis in spherical coordinates, they move in different points, they point in different directions, right? For the radial, the point in the vector point in the radial direction moves as I move around R3, right? It's pointing to different directions depending on the point. So there is the vector of the basis is a vector field indeed. It's not a constant vector in the whole of space. So if I were to take this seriously, I should have done the following. Instead of doing that, if I were to take something like, let me put it in quotes, right? Because we're trying to make sense of an object. If I were trying to do something like this, I would have to do two things. I would have to do Leibniz rule on this, right? Is certainly the derivative of the vector, the component with respect to mu, epsilon element of the basis nu, plus then the component as it was, and then if you want, let me write like this, the derivative of the vector with the vector of the basis with the point x mu. I would be missing this bit. Then you see, of course, that if you're in Cartesian coordinates in Rn, right, for example, you know that the components of the vector will change, but the vector of the basis don't change. They're the vector of the basis is the vector 1, 0, 0, 0, 1, 0, 0, 0, 1, and they don't change with the point, they're always the same. Whereas in, for example, spherical coordinates, they would change with the point. All right, so the one thing is that the derivative of a vector field like that, so if I have a vector field, say, x, 1, y, right, if I take the partial derivative of this with respect to, say, x, this thing is going to give me 1, 0, 0, which is still a vector, right? So the partial derivative with respect to the coordinates of the vector field, epsilon mu, can still be expanded in terms of elements of the basis. So I can write this thing as partial v nu, partial x nu plus, and now I have v nu as I was, and then I write here a linear, I'm going to express this thing with the two indices as an arbitrary linear combinations of vectors of the basis. So let me write perhaps rho nu mu, right? And then elements of the basis, epsilon rho. So all that I did here is saying, right, whatever this object is I should be able to write it in terms of an expansion in elements of the basis still. This object, of course, contains all the possible information of how this derivative acts on the vector of the basis. It tells you, if I act on the element of the basis nu with respect to the coordinate, the partial derivative with respect to the coordinate mu, the muth coordinate, then the rho component of what results is this gamma coefficient that I wrote here. Now, a last step that I can take is to say that I can take a common factor of this by changing the dummy indices. So let me call the index nu, that's easy here, so I can do partial v nu partial x mu, and then I take the epsilon nu outside, and now I'm going to change the index. I'm going to call this one v sigma, and then this is going to be a sigma. I'm going to call the rho, this is the second one, a sigma. I'm going to call the rho nu, and the mu, I can keep it as it was. So I get here, this is a common factor, epsilon nu, for both of them. I just did a change of dummy indices. So I got that this object, partial v, partial x mu, has this expression, you see, so the equivalent, the intuitive equivalent for the variation of the function in the manifold, as I move around the manifold, right, the partial derivative with respect to the coordinates, if I apply to a vector field, I'm going to have to add some extra term that comes from the variation of the elements of the basis. Not just, remember, it's a Leibniz rule, right, in a way. You have a change because the coordinate change of the vector field as you move, but also the vectors of the basis change as you move around the manifold. Now, this thing here happens to be what this thing is missing to transform like a tensor. In fact, a nice exercise for you to do, that is actually everywhere in notebooks, you can find it everywhere, but I think it's nice if you practice it, is try to transform this object under a change of basis and see that it's not a tensor. And now add this and see the whole thing, how it transforms under changes of basis, and when you add that, you find that the object transforms as a tensor, actually. So this thing is what this thing is missing in order to be a tensor. And what is missing is the fact that, well, not only the vector field changes when I move around the point, also the vector of the basis changes when I move around in the manifold. All right, so this is the idea, and this, in fact, we're gonna call the covariant derivative of the vector field V. That's what we're gonna define as the covariant derivative of the vector field V. We're gonna do it more rigorously, but I hope that the idea is clear of what this is. The covariant derivative is taking the variation. It's like taking the gradient, but not just the gradient of a function, the gradient of a vector. If you remember from your calculus, when you take the gradient of a vector, you get a matrix with the possible variation of all the components of the vector in all possible directions. So you increase the type of the tensor, you go up one in the type of the tensor, you add one covariant index to the tensor, and it's basically, when you apply it to a vector, takes into account not just the variation of the components of the vector in a given basis, but also the fact that the vectors of the basis are vector fields themselves, and they change with the point. All right, now that we've gotten the idea, more or less, of why we need a covariant derivative and what is this notion of the covariant derivative, let's define it a little bit more rigorously. All right, let's be a little bit more rigorous in the definition. Let me talk about an affine connection that I notate as with the character nabla. It's a rule through which we assign to every tensor field T, that is R times contravariant and R times covariant, and components in an arbitrary basis, let me just call it DC, etc., DE, etc. for the covariant ones, we associate, using the affine connection, another tensor field, which I call nabla T, that is one more time covariant, whose components I notate as follows. I get the nabla A, right, and then acting on the tensor. I actually would probably many times call this just the gradient of T. And typically also notated with a semicolon. You will see it notated as a semicolon as well. And we call that new tensor field, that is one more time covariant, we call it the covariant derivative of T. And we make it so that we want to generalize the gradient to something that is not just functions. So we impose the following four properties for the covariant derivative. We want it to be linear and satisfy Leibniz rule. Right, we want it to be a derivative. Then we want to commute with the contraction. We want it to be compatible with the tensor nature of what you're applying it to. And so that truly adds a covariant index. And I wanted also that over functions is just the differential. Why? Because I already know that the differential of a function is the gradient of a function. In fact, as we discussed in the first innocent example that we considered to justify the need for a covariant derivative, we already know, it's the only one that we unambiguously know how to take the gradient, right? How to define a gradient. So if you find me a rule that does that, satisfying these four properties, you get me a covariant derivative. How many of them are there? Well, infinitely many. There's not a unique way of doing that. There are given a differentiable manifold, I can define infinitely many covariant derivatives that are different and not compatible with each other. This is going to be important because the notion of curvature is going to be related with another notion that we need to define called parallel transport, and that is going to be related with the connection that we have, with the affine connection that we have, with our covariant derivatives. All right, we haven't yet say how we define it, but once we have defined one, we can also define the directional covariant derivative of t in the direction of v, which is we notate as nabla v t, which is a tensor of type Rs, same as the original t, which is okay, then get the covariant derivative and contract it with the vector. So this is, it might remind you, even though we don't have inner products or anything, it might remind you of this, right? When you took the directional derivative of a function, add with the gradient, and then contract it with the vector v in which you want to take the direction of the derivation, right? So this is indeed the generalization of the gradient to arbitrary tensor in a differentiable manifold. And surprise, surprise, because we are generalizing to tensor, etc., there's no single way of doing it. There are some four things that we'd like it to have in order to represent what we want it to represent, but it's only univocally defined for functions. All right, then how do I characterize a different connection and therefore the different covariant derivatives that it defines? Well, like this. The coefficients of the connection. Now, the coefficients of the connection gives you full information about the covariant derivative and the affine connection. It's what defines the affine connection. So the coefficient of the connection basically tells you how the covariant derivative acts on the elements of the basis in all possible directions. You can tell. The coefficients of the connection tells you the value of the directional derivative in the direction of the element of the basis, C, the cth element of the basis, of the bth element of the basis, and the component eighth in that basis, you see? So it tells you all the direction. It's like if you compute the gradient of a vector and then you ask, sure, it's a matrix and the matrix has the information about the variation of the component x of the vector in the direction x. The 1, 2 has the 1, 2 component of the matrix has the information of the variation of the x component of the vector in the direction y, and so on and so forth. So you see that matrix contains all the information. Well, this object, right, this 3-index object contains all the information of all that what the covariant derivative can do. As you can tell, let me repeat, is the covariant derivative of the bth vector in the direction of the cth vector, component A. So that fully characterizes the action of the covariant derivative on the basis of the tangent vector spaces, and therefore allows us to compute the expression of the covariant derivative of all tensor objects as long as I know the coefficients of the connection. Before we continue, let's talk a little bit about the convention used for the coefficients of the connection in this course and how it relates with other conventions that you may find outside of the course. Now, we define in this course the coefficient of the connection A, B, C as the action of the covariant derivative on the vector of the basis B in the direction of C and the component A of the resulting vector. This is the convention of the first line of the screen that you're seeing right now. This is the one we will use. Now, this definition is different from a different definition that is very, very common in the literature and that we display on the second line of the screen that you're seeing right now. And it's characterized because in that convention, the coefficient of the connection ABC is defined as the covariant derivative acting on the cth vector of the basis in the direction of the bth vector of the basis, component A of the resulting vector. These two conventions are actually okay to use as long as you're consistent. Let's just remember that we're going to use the first convention, the first line convention in this course, and then there are references out there that actually use the second one. Later in this video, we will discuss that under some conditions and in some particular bases, the coefficients of the connection are symmetric in the two lower indices, which means that the two conventions are equivalent. This will be the case in most of the calculations of general relativity, and that's why in general relativity courses they don't really care much about the order. In any case, this is not the case yet, so let's keep in mind the convention we use, and let's go back to the main video. Now, from this relation, we can write what is the value of the covariant derivative component C of the element of the basis B. How? Well, very easy. From this expression, this on the right hand side, this on the left hand side, then I multiply by epsilon sub A, the dual to that element, right, on the left and on the right, and that gives me exactly the following. This is gamma A BC epsilon A. All right, so this, as you can tell, this expression tells me what is the cth component of the covariant derivative of the vector of the basis B. Now with this, we can obtain the expressions of the covariant derivatives of functions, vectors, and tensors and one forms, right? Let's do it manually for vectors and one forms, and then let's write the general formulas, and let's write them in a coordinate basis, actually. All right, so we know, and remember, we already know what it is for a vector, for a function, right? Because it has to be the gradient, has to be the differential of the function. So I know for functions, let me write the covariant derivative in the direction of the vector w of f. But I do know that the covariant derivative of f is exactly the differential of f. Therefore, the covariant derivative in the direction of w, which is the contraction of the differential of f, let me just write it here. This is the contraction of the differential of f with w, right? That gives me w on f, the directional derivative of f, of course, from the first videos that we recorded. Now, in a coordinate basis, so I can pick w to be, let's pick w to be an element of the basis of vectors, like, for example, epsilon a, right? And that means that the eighth component of the covariant derivative of f is exactly equal to epsilon a acting on f. I can do it with all, I can do it with all the elements of the basis, and I know that all the components will be that, all right? And in particular, in a coordinate basis, let me write
in a coordinate basis.
I know that the action of the elements of the basis is the partial derivative, so I know that the partial derivative of f, well, let me call it mu, because now I know it's a coordinate basis, will be equal to partial mu f. And that's kind of the one that is most useful to remember for our purposes. So this is the abstract expression, and then we write it in an arbitrary basis, and then we write the expression in a coordinate basis. All right, let's do it. Let's compute it for vectors, right? Although with vectors, remember at the beginning of the video, we did something not hand-wavy, but kind of to try to understand the concept of variation of a vector as I move, a vector field as I move in the manifold, and it has to change because the components change, but also because the vectors of the basis change. We already got an expression, right, for that. We're gonna get it as well here, but operating a little bit more rigorously. Now for a vector field, I'm gonna write directly the directional derivative in the direction of the vector of the basis epsilon c of a vector field v. And I'm gonna write this vector field in terms of an expansion in elements of the basis. So that would be v epsilon b, right? Wonderful. Okay. Now, I use Leibniz rule here, and I'm going to get the directional derivative in the direction of c of the component, and then this contracted with the element b, and plus the direction v b, and then the directional derivative in the direction of c of epsilon b. This is the action, the first one is a function. You treat this is the component, which is a function, right? The components of a vector fields are a function in the manifold. So this is the derivative of the function in the direction of c, which I already know what it is. It's going to be the action of, well, you want the action of the element of the basis on that function. So this is going to be epsilon c acting on vb, contracted with epsilon b. And I'm going to have to add vb, and now this expression I already have here. All right, so this expression is going to be epsilon gamma a bc epsilon a. All right, Now all that I have to do now is change the components because I want to have a common factor b or epsilon b perhaps here. So I'm gonna call, yeah, maybe what I should do here is call this one a, all right? And then this is equal, so I get the common factor epsilon c acting on VA, right? And then that gets me, common factor, plus VB gamma A B C contracted with epsilon A. All right, so I can write the components. From this expression, I have this equal to that. So the component equation is just nabla C V, and let's call it as I have here, VA is going to be equal to epsilon C acting on VA plus VB gamma A B C. All right, those are the components. Now, these labels may not be the most elegant. Maybe you want to have AB just for consistency. Let's change the name. I'm going to do the following change. C, I'm going to call it A. A, I'm going to call it B. All right? And then the dummy index B, I'll call it the dummy index B. I'm going to call it, I don't know, C, right? Why not? So I'm going to implement that change here, which is a change of indices, which does nothing to the expression. Done. And I don't need this anymore. And then in a coordinate basis, all that I did is aesthetics, right? Because I just wanted to have AB and AB as the first two indices, but it's exactly the same expression as I got before. And now I do, in a coordinate basis, I know that the elements of the basis act on functions by taking the partial derivative. So in a coordinate basis, I'm going to call A mu, because a coordinate basis, B nu, it's equal to the partial derivative mu, right? Mu plays the role of the A, of V B, that is nu, right? Plays the role of the B, plus V, the dummy index, let me call it sigma perhaps, and then gamma nu, sigma, and then the A is mu, right? So this is the expression in a coordinate basis, and this is the expression that we will use the most. If you know the coefficients of the connection, it's very easy to compute the covariant derivative of a vector field, like this. Those are the ones that we will actually use in the rest of the course, because we will work a lot with coordinate bases. All right, now we should also obtain the covariant derivative of one form, at least, and then before telling you what is the general form for tensors. Now, to get it for one forms is actually rather easy, because we can just apply we can operate already in components, and we can apply the covariant derivative to the contraction between a one form and a vector, and I know what the result of this has to be. This is a scalar, right? It's a function. So it's the components of the covariant derivative of a function. It's something like this. So I know that the result has to be, this thing has to be the vector A of the basis acting on omega B VB. All right? On the other hand, I can apply Leibniz rule, and that tells me that this thing is going to be covariant derivative with respect to A of omega B contracted with VB, and this is what I want to know, plus omega B covariant derivative with respect to A VB. Nicely enough, I know what this is. I computed it. I have it right here. So I substitute, and I have nabla A omega B VB plus, and then substitute omega B times this, which is epsilon A VB plus VC VCA. All right, wonderful. Now, I know that this is a derivative, right? So this thing still, I mean, the action of the vector, of a vector of the basis on, a vector is always a tangent vector to a curve, it's a derivative, it takes the derivative of this. So as such, satisfies Leibniz rule, so this thing is equal to epsilon A omega B times VB plus omega B epsilon A VB. All right, so now we need to compare. On the one hand, what do I get? Now I get the terms that I have: omega B epsilon A VB. Ah, nice. This is here as well. So let me just write. Maybe I should write the equality right here. and I have the equality epsilon A omega b VB plus omega b epsilon A VB. Okay. All right, so the terms that I have here, this term right here cancels with this term. All right, so let's write the whole thing, and we're gonna do some gymnastics with the indices. Let me just continue this equality here. Let me put on the left nabla A omega b contracted will be VB, and that's gonna be equal to, and I put on the right hand side I have epsilon A omega b VB, and then this term here with a minus omega b gamma BCA, and I'm gonna put the V after. All right, one thing that I may want to do, I have a dummy index C here that I may want to call B, the same as this guy. So to do that, I can play with the dummy indices. These are all, even though my handwriting is poor, these are all dummy indices. So they're all summed, except for the index A. The one index that cannot be changed is the index A, right? So I'm gonna change, unless I change it also here. But the dummy indices I can be changed independently, they're just summed. This one, I think I'm gonna do a swap, B swapped with C in this sum. Let's do this swap of, both are dummy indices, you see, so I can swap them, they're summed. All right, this is a typical thing that sometimes students, the first time they start doing index notation, have troubles with. And you may think, but there's a B in here. No, there's not a B. When it's contracted, that index is not, there is a sum over B, or so over Joshua. And here, there's another sum over C and over B. I can change those indices no matter what, when they're contracted. I have to be careful though, I cannot change A. A is the only real index on every side here. All right, the nice thing is that allows me to take a common factor, and then finally write, or semi-finally write, nabla A omega B VB equals epsilon A omega B minus omega C gamma CBA, and then all multiplies VB, okay? And that means this is true for all B's. I picked an arbitrary B in here, so I can just equate this thing to this thing, everything that's contracting with B, and that gives, the result I want. Just I'll write it again, okay. So nabla A omega B, so the components of the covariant derivative of a one form are equal to epsilon A, element of the basis acting on the component, right, minus omega C, contraction with a coefficient of the connection CBA with a negative sign, right? And now I can do it in a coordinate basis, and in a coordinate basis, again as before, in a coord basis, I get that, let me just call it mu and nu, nabla mu omega nu, it's equal to, then of course the action of epsilon, it would be of course epsilon mu, but you know that that's a partial derivative when it's a coordinate basis, so it will be partial derivative with respect to mu omega nu minus, and now omega sigma gamma sigma, and then B was the nu and A was the mu. All right. So this is the covariant derivative of a one form in a coordinate basis. The components of the covariant derivative of one form in a coordinate basis. Notice the difference in sign. So now that we have done this, we can write the general expression for tensors. Let me write it for three different kinds of two tensors, but the rule, you kind of see, you can get all of them and you can kind of see already what the rule is going to be, right? The rule is, per contravariant index that you have, 1 plus term the object that you have contracted with the coefficient of the connection. And per covariant index that you have, you're going to have to subtract it instead of adding. That's the rule, that you get using exactly the same logic. Let me show you the expression for other kinds of tensors, but the logic is the same and the way to derive it is the same. All right, so directly in a coordinate basis, components of the covariant derivatives in a coordinate basis epsilon mu. All right, so we have here the components of the covariant derivatives already in a coordinate basis for different kinds of tensors, just for you to know that the pattern that we computed repeats, and in what way it repeats, right? We have that the covariant derivative of a function is just the partial derivative of the function, if you want. we have the covariant derivative of a vector has this extra term with the coefficients of the connection. And remember where they came from. This one comes from the variation of the components as I move in the manifold, and this one comes from the variation of the elements of the basis as I move from them through the manifold. In a way, like twisted because of I'm using a curvilinear coordinates, or because I have curvature. Same goes with one forms. With one forms, we actually found that the terms that go with this a minus here, and the way in which it contracts, the structure in which it contracts is clear here. You contract the first lower index of the coefficient of the connection with the components of the vector, and the upper index of the coefficient of the connection with the coefficients of the one form. And now if we want to do tensors of higher order, well, you add or subtract the corresponding terms in the same way. You can tell here how you do it with a tensor that is twice contravariant. So you add one term for the first index, first with the index alpha is the one that's contracted with the coefficient of the connection, and then is the second index, the one that's contracted with the coefficient of the connection. First, the first index, and the second index. Now, one contravariant, one covariant. Well, the contravariant ones is the first index, you contract the first index, and then you add with a minus the one that contracts with the second index. And if both indices are contravariant, a twice contravariant tensor, then you add two terms. One first contracting with the first index, and then contracting with the second index. So the pattern is clear, and I think it's trivial now to add the order, whatever order you want of a tensor, computing the covariant derivative. And now you know, given the coefficients of a connection, you know how to compute covariant derivatives. Before we see an example, let's talk about one more thing. A gamma has three indices. One, what we would call a contravariant index, and two, what we would call covariant indices. However, I want to make the point that not everything that has indices is a tensor. And in particular, the coefficients of the connection are not a tensor. Not a tensor. Let's see, to prove that it's not a tensor, we just need to prove how it changes under changes of basis, right? And if it's a tensor, it's to change in a particular way. It's to change with one lambda per covariant index and one lambda tilde per contravariant index. Well, let's see if that's the case. Now, I wrote here the coefficient of the connection from the definition, and here the coefficient of the connection in the prime basis using the change of basis given by this. Now, I can do two things. From the linearity of the contraction, I can take this one out. That's not a problem. I can take lambda tilde a prime a, all right? And then I can decompose this in two terms, right? The first one, I'm going to use Leibniz rule here. So the first one is going to be epsilon a, comma, and then let me apply to the second one first. This is going to be lambda beta prime beta, and then I get the covariant derivative in the direction of lambda c prime c epsilon c, all right? And then here epsilon b. Right. I get epsilon a acting on, and then I get the epsilon b gets out. I'm going to have the lambda of, and in the direction of c prime c, epsilon c, all right. The lambda b prime b, epsilon sub b. Let's work out what this thing is. So this thing, right, is the directional derivative in the direction on the epsilon prime of epsilon b, right? So what is this? This thing is the contraction of c prime c, c, epsilon c, right, with the covariant derivative of epsilon b, right? But now we can use, this thing is this, right? This thing is this thing. But now we can use the linearity of the contraction and take the c prime c out of this, right? So we have c nabla b. All right, but what is this then? This is the all covariant derivative with respect to, let me write it here. So this is lambda c prime c, and then this thing is the covariant derivative in the direction of c of epsilon b, right? All right, so all this thing is just I can take a lambda out. All right, so let's just summarize it here to avoid mess. This is what we just proved, which is nice. So that means I can take the 3 lambdas. For the first time, I can take these 2 lambdas out. So let me write the 2 terms independently. The first term is going to be lambda tilde a prime a multiplying lambda beta prime b, so b prime b, lambda c prime c, multiplying epsilon a, covariant derivative in the direction of c, epsilon c, of epsilon b. That's the first term, and this is really nice because this thing is exactly the coefficient of the connection. So we can substitute this thing by the coefficient. Let me just write it here. I mean, I'm missing something here, right? But let me just write the next step already. So this would be lambda tilde a prime a, lambda b prime b, lambda c prime c, the coefficient of the connection a, b, c. If this were the only term, then it would transform as a tensor, no problem. Unfortunately, we do have another term in here. Now, what is this term? So this term is, first let's evaluate the covariant derivative or the direction lambda c prime c, epsilon c, of lambda b prime b. So this is the directional derivative of a function. So this is nothing but lambda c prime c, epsilon c, acting on the coefficients of the change of basis, the lambda. Right? And this action, if it were, for example, a coordinate basis, this would be a partial derivative, right? Is the directional derivative in the direction of this vector of the basis. So knowing that, it's easy now. This thing is a number now that I can, because of the multilinearity, this is no longer a vector, it's the action of a vector or a function that is a number, it's a scalar. I can take it out of this product, and then this becomes, let's call this A, just for illustration, A becomes, let's write it here. I take this number out, lambda c prime c, epsilon c, acting on lambda b prime b, and then this is just the product epsilon a, epsilon b. Right, and I know what this is because this is a delta. These are dual bases, right? So this is delta AB. And because it's delta AB, that what I get is that this thing is lambda c prime c, epsilon c, acting on lambda, and now changes the b by an a, b prime a. All right, so knowing that, let's substitute. This is the whole element here. Let's substitute another missing product in here, and let's see what we get. All right, so plus, let me add this term. So I have the lambda tilde a prime a. Good. Then I also get lambda c prime c. And then I get the action of the vector epsilon c on the lambda b prime a. All right, and I can erase now this garbage, so I don't need anymore. And then we know that this thing is this, right? And this thing is an extra term. So if it was only this term, then the coefficients of the connection will transform as a tensor. But because they have this extra term, they don't transform as a tensor. Sadly, the coefficients of the connection are not tensors. So you see, having indices does not guarantee that you're a tensor. Because yeah, you kind of almost are a tensor, but no, in the end you're not, because you have this extra term. There's something interesting to notice though. The extra term does not depend on the particular connection you chose. You see, let me just write here what it is, the whole thing. Let me write the whole thing. Plus lambda tilde a prime a, lambda c prime c, epsilon c lambda b prime a. Now, this part depends on the particular connection that you chose, that's why the coefficient of the connection, but this one doesn't. This thing is the same for all connections. Now, interesting enough, if I pick two connections, imagine that I create two connections, gamma A, B, C, and then another connection, gamma tilde, different values, A, B, C. If I subtract the two, this part would be linear, the difference of the two connections, and this part will disappear. So the difference between two coefficients of the connections is actually a tensor. The coefficients of the connection are not tensors, but the difference between two of them is a tensor. This is interesting and also has repercussions. All right, finally, we're gonna say that an affine connection is symmetric or torsion-free if and only if it acts symmetrically on functions. This is the definition of a symmetric connection. So covariant derivative AB of f is equal to covariant derivative BA of f. One can prove, and it's a lengthy proof, but a proof that you can do, and I leave as an exercise. In fact, I will give you 1 point out of 100 if you send me the proof, if you prove it and show me. If the connection is symmetric, it is satisfied that you can express the contraction of the coefficients of the connection with a vector of the basis. Anti-symmetrized, it's equal actually to the Lie bracket of the elements of the basis, like that. And in particular, that implies that in a coordinate basis, the coefficients of the connection are symmetric in the two last indices, in the two sub-indices. Now, for the grand finale of the video, let's do an example in R2, just to get familiar to how to do operations in a concrete case. Let's have some fun with R2. I'm going to give you two coordinate bases. One is the Cartesian basis, the other one is the polar basis. And it's going to be fun because we're gonna discuss how the basis that you actually use in your physics courses in the past is probably not a coordinate basis because what you usually call polar coordinates, or at least the way in which you apply unit vectors of polar coordinates, is certainly not a coordinate basis. It's kind of embarrassing, and that's why you have to correct things and add the funny elements to the funny terms to the gradients and things like that. Huh? But okay, let's see step by step. Let me give you two proper coordinate bases. Let's consider the Cartesian one and the polar one, right? And those are the coordinate bases associated with the following coordinates that you already know, right? Polar coordinates, so the usual polar coordinates of R2. All right, so I want I'm asking you to find the coordinates of the vector of the basis in the radial direction and the vector in the angular direction. And what are the coordinates of those vectors in the xy basis? How do I find that? Well, the change of basis matrix, lambda, right? So I know, of course, that epsilon, let me call it mu, right? Epsilon mu would be equal to lambda mu nu epsilon nu, right? So I know, in particular, let's do the x, for example. I know that epsilon, I'm going to do r. Epsilon r is going to be equal to, and then mu is r, so r, and then x, epsilon x, plus lambda r, y, epsilon y, right? That's the change of coordinates matrix. Now, we need to compute the change of coordinate matrix. The same way, I'm going to write here, epsilon theta, it's equal to lambda theta x epsilon x, right? Plus lambda theta y epsilon y. So you see, instead of using numbers, mu equals 1, 2, the labels 1 and 2 I identify with x and y, and the labels 1 and 2 of the prime coordinates I identify with r and theta. All right, and this is the Einstein sum, right? Okay, so we need to find those matrix elements, but that's easy, right? Because I know that lambda mu nu, it's equal to partial x nu, partial x mu prime, right? Then we know that lambda, let's just compute it here, right? Lambda, we're gonna do Rx is gonna be equal to partial x, partial r, which is just the cosine of theta, right? Then I compute lambda, let's do Ry, and this is partial y, partial r, and that is sine theta. Now, let's compute lambda theta x, and that thing is partial x, partial theta, and that thing is minus r, sine theta, and lambda, finally lambda theta y, which is partial y, partial theta, which is r, cosine theta. All right, so now that we have these coefficients, we can compute finally the coordinates of the vectors in the polar basis in the Cartesian basis. So we substitute and we get And we get that, which is the answer to the question I asked. All right, let's keep this and let's ask a different question now. Finding the coefficients of the connection is as simple as evaluating this expression. This is a coordinate basis. So in a coordinate basis, remember that we could understand this as what are the proportionality coefficients in terms of the elements of the bases themselves of the variation of the elements of the basis with respect to the coordinates, as in the first example, in the first idea about the covariant derivative that we saw at the beginning of the video. All right, so all that we need to do is evaluate derivatives and see what we get. All right, the variation of epsilon r with respect to r. Well, remember that epsilon x and epsilon y are constant vector fields. They always point in the direction of x and y. They don't change with the point, so there's no variation of them. The components can vary with the point. In particular, the components of r don't vary with r, so the derivative is 0. This is equal to 0. So that tells me right away that gamma r equals gamma theta r equals 0. There we go, first one. All right, what about theta? Well, if I compute the derivative, let's just compute it here. Partial epsilon r with respect to theta. What is that? Well, the cosine gives me the minus sign, so minus sine theta epsilon x plus cosine theta epsilon y. But if we compare with epsilon theta, we see that it's almost there, only divided by r. So this thing is epsilon theta divided by r, right? Wonderful. So because this thing is epsilon theta divided by r, I know that this coefficient is 0, there's no epsilon r, so that implies that gamma r theta equals 0, and gamma theta r theta equals 1 over r. All right, by comparison. So let's compute partial epsilon theta with respect to r. That's pretty easy. That gives me minus sine theta epsilon x plus cosine theta epsilon y, right? Which is exactly the same thing as before. Epsilon theta divided by r. Okay, well, this thing is epsilon theta divided by r, and that means the coefficients of the connection are r theta r is 0, there's nothing multiplying epsilon r, and there's 1 over r multiplying epsilon theta. Aha, so we're finding that, look at that, the coefficients of the connection are symmetric in these two indices. I wonder why. This is because it's a coordinate basis. And as we discussed right before, for a coordinate basis, the coefficients of the connection are symmetric in the two lower indices. Now let's do the final one. The final one tells me, like, okay, I need to compute partial epsilon theta, partial theta. Okay, so what is that? That gives me minus r cosine theta epsilon x minus r sine theta epsilon y. Now, if we compare it, this is like epsilon r, only with a minus r multiplying. Okay, so this is minus r epsilon r. All right, well, in that case, we finally found, let's just write it here, minus r epsilon r. So that means that gamma r theta theta, it's equal to minus r. And finally, well, let me write it here, gamma theta theta theta, theta theta, it's equal to 0 because there's nothing multiplying epsilon theta. And there you go, the coefficients of the connection for polar coordinates in R2. How cool is that? All right, so now we learn how to compute coefficients of the connection for a particular case. Now that we know that, let's have a final question that connects with the notion of coordinate bases versus non-coordinate bases and things that you do in calculus. So I'm going to ask a question. I'm going to ask, is partial r partial theta a coordinate basis? We know that partial x partial y are. Remember that the necessary and sufficient condition is that the commutators are 0, right? Partial x partial y, the commutator is 0. Therefore, it's a coordinate basis. How about partial r and partial theta? Is that 0? Well, I mean, it is, but let's just prove it. Let's just prove it by brute forcing. Why not? So let's just write it fast. All right, so I computed the commutator between partial r and partial theta, and I substituted the expression of the vectors of the bases in terms of the Cartesian coordinate bases. And I use the fact, of course, same as before in the calculation, partial x and partial y are constant vector fields. They all point in the same direction in all points of R2, right? Using that, we get exactly that this is a coordinate basis. Nice. So polar coordinates r and theta define a coordinate basis for the vector action. So polar coordinates r and theta for R2 define a coordinate basis for the space of vectors in R2 that is partial r and partial theta. But are these the ones that you use in electromagnetism and everywhere else in physics all the time, and in calculus that you've seen, in vector calculus that you've seen? Well, not quite. Why? Let's compute the norm of this vector, shall we? I mean, again, in the differentiable manifold so far, we don't have a notion of norm, we don't have a notion of inner product yet. But in R2, we do have a notion of dot product, right, of inner product, and a notion of norm, and we can talk about, are they unit vectors or not? Remember, in differentiable manifolds, not yet, we haven't gotten there, we need a metric for that. But in R2, we do have a metric, in R2 we have the dot product as well. All right, so let's see, just out of curiosity, to understand a little bit better calculus. So what is epsilon r dot epsilon r? Well, that's easy, because this is cosine squared theta epsilon x, right? Plus sine square theta epsilon y, right? Plus the cross terms, I don't know if I should write them because they're zero, but let's write them. But these are zero because they're orthonormal actually under the dot product, right? The vector in the direction of x and the unit vector in the direction of x and the unit vector in the direction of y. And these things are normalized to 1. So this is 1 and this is 1. So this thing is certainly 1. So the norm, and again, this is something that we are writing because it's R2, not because we have seen this yet in differential geometry, but the norm of r, of epsilon r, is 1. What about the norm of epsilon theta? Well, let's see. This thing is going to be, let me just write, the cross terms I'm not going to write because we know they're zero. Let me just write the ones that, this one, minus r sine theta times epsilon x times minus r sine theta epsilon x. That gives me r squared sine squared theta epsilon x, right? Plus r squared cosine theta epsilon y, plus the cross terms that are also zero, right? But what is this though? That is r squared. Oh my, the norm of epsilon theta, it's r. It depends on the point, and it's not 1 in general. All right, you see, the coordinate basis vector partial theta is not normalized to 1 under the inner product that R2 has, the dot product. So far, in differentiable manifolds, I would say, so what? I mean, because we don't have an inner product, we haven't talked about an inner product yet. But here in R2, it kind of matters because in physics, you kind of want to multiply your quantities. You want your vectors to give a sense of direction and the magnitude of the vectors to reflect a physical quantity, right? So you better use unit vectors. Can I use unit vectors? Well, yeah, you can normalize, I guess. I can define let's define a new basis. The new basis, I'm gonna call it epsilon r prime, which I'm gonna make equal to epsilon r, and then epsilon theta prime that I'm gonna make equal to epsilon theta divided by r. And then we're fine, no? Because we have an orthonormal basis now, they're normalized. Yes, you have an orthonormal basis, but you've paid a price. You know what the price that you paid is? Let me show you. So with this definition, I can compute now the commutator between the vectors, right? I can compute the commutator epsilon prime r, epsilon prime theta. And look what I get. So epsilon prime r, epsilon prime theta gives me this operation, right? Because this is the derivative with respect to r, and this is the derivative with respect to theta divided by r. And if I compute the commutator between the two, what I get is, this term cancels this one. What I get is partial theta divided by r squared, which is different from 0. So the normalized, if you want to normalize polar coordinates, the vectors, the vectors of that come from polar coordinates to define a basis for the vector space in R2, then if you normalize them, you lose that they are a coordinate basis. And that price that you pay makes complicated talking about gradients, divergences, and Laplacians and things like that. And that's why you have to add some crazy factors to it when you actually operate outside of a coordinate basis to compute gradients. This is the reason, because you are not freaking using. So most of the time it's like, are you stupid? Use a coordinate basis. Don't complicate your life because everything is simpler in a coordinate basis. Well, sometimes, like in polar coordinates or spherical coordinates, you don't use coordinate bases. Why? Because I want my vectors to be orthonormal, not just orthogonal. I want it to be normalized to 1. Well, then be my guest and pay the price of not using a coordinate basis. And now hopefully you understood one more thing about why when you were like, whenever they taught you vector calculus, you maybe think, oh, complicated. Why do you have all that? Yeah, sure, the vectors have to change like this, like that. And you see like long derivations to justify the expressions for the gradient in polar coordinates and in spherical coordinates. Well, you know why now. You're kind of shooting yourself a little bit in the foot. I mean, for good reason, because you have good reasons to use it, but still, it's not a coordinate basis. Cartesian is a coordinate basis. Partial or partial theta is a coordinate basis. The vectors that you actually use that are orthonormal in the direction of r and theta, they are not a coordinate basis. All right, this is it for the video. In the next video, we're going to use what we learned here to talk about the notion of parallel transport, the notion of geodesics and geodesic curves and geodesics, and the notion of curvature. Until then, take care.